small group. Oof. Yeah. So if you want to stop me during my talk and just ask me questions or whatever, I think we can just keep it more conversational than anything else. And if there's a huge, maybe science question, we can keep it for the end. So yeah, today I just wanted to talk about some of the work I've done to try and quantify the mechanics of our earthquake start using a combination of rock mechanics and some novel experimental seismological techniques in the lab scale. And yeah, as I was saying, just had this picture here to rein us in into the overarching societal relevance of why we care about these types of questions and so on. And I noticed for this audience, maybe I don't need to start with what earthquakes are, especially considering the lineup of the previous speakers you've had. I noticed you have had Greg McClaskey from Cornell at some point during the seminar series. And so I kind of wanted to start with talking about the earthquake nucleation process. Maybe he showed this figure, maybe not, but this is actually from one of his papers from 2019. Where I think it's a really nice conceptual cartoon that shows what happens when an earthquake is just about to begin, right? So this is the nucleation process. And in my view, it's both incredibly important and really difficult to identify or quantify in the Earth. And so in this cartoon, we have some distance dimension on the x-axis on the fault and time increasing on the y-axis. So the prevailing view is that when you have strain accumulating, the fault is slipping very slowly before an earthquake. And this period can also have foreshocks or aseismic creep, small earthquakes, all that, leading up to the big event, which is the green stuff here. So when the slow creep events and foreshocks start to happen on a patch larger than a critical size, which is LC here, sometimes you'll see also being referred to as H star, which is a critical nucleation length scale. And we think this is of the order of centimeters, meters, kilometer in the lithosphere. That's still an outstanding question as to what LCC is in the Earth's crust. So when these foreshocks and aseismic creep coalesce into something that is larger than LC, then the event grows uncontrollably into a large earthquake, which ruptures a big chunk of the fault in green. So that's the prevailing view. And I want to address a couple of questions in my talk today. That's what I've divided the science into. The first part, I'm going to be talking about the seismic signature of the earthquake nucleation process. And in the second part, I'll touch a little bit upon some of my more current work, which is trying to understand a little bit more about the mechanics of slow slip events, and specifically asking the question of what makes a slow slip event slow. So for the first part, I had the really wonderful opportunity to collaborate with a number of folks at Penn State, Chris Marone in the geosciences department, Jacques Riviere and Parisa Shikui, who are professors of applied and engineering mechanics at Penn State, and Chas Bolton, who was a grad student at Penn State and is also a postdoc now at UT. So just to give some idea about the nucleation process and precursory deformation before earthquakes, I want to give you a couple of different, very different examples before a couple of very large earthquakes. So for example, this is a nearly 8-month-long precursory slow slip and triggered seismicity that was leading up to the 2014 magnitude 8.1 Iquique main shock in Chile. There was a very long slow creep on the subduction plate interface. There was some intense foreshock activity, which are all the orange and the green patches. And finally, all of these culminated in the magnitude 8.1 earthquake that ruptured the interface. And just this cartoon of this subduction interface, you can really see how remarkably similar to our theoretical earthquake nucleation process this is. Now, another really well-documented case of pre-seismic activity occurred before the infamous 2011 magnitude 9.1 Tohoku earthquake in Japan. And this is a map of Japan on the left, and this star is the earthquake hypocenter. The black curves are slip contours of the Tohoku main shock, and the plot on the right is a time lapse of the Gutenberg-Richter p-value, which is a frequency magnitude statistic of earthquake distributions over time leading up to the Tohoku main shock, which is the red dot here. So the p-value, like I said, is a logarithmic quantity of earthquake productivity. And so if you have a p-value of 1, it means that you have 10 times as many magnitude 5 events as magnitude 6 events, and so on, right? So what we see is that there is a decade-long reduction in the earthquake p-value, meaning that leading up to Tohoku, there were fewer earthquakes in the region, and relatively, they were larger than they were in the past. So just to quickly summarize the few slides that I've showed you, or what I've said so far, is that we think precursory deformation signals can contain some information about the systematics of a future event. They definitely contain information about the nucleation process. So it begs the question of, if they're that great, why we don't use them all the time. And there's a couple problems with that, right? First, oftentimes, I gave you a couple of examples of pre-seismic signatures before earthquakes. They are relatively rare, and we don't know if that's because we don't look for them properly or if they simply don't exist. And we also, secondly, only think to identify or look for precursory signatures after an event, rather than continuously all the time. And third, even if we did spot them, we don't know until the event happens if they were precursors, and we don't know the physics behind these signals. So it's really hard to understand what we're seeing. So this is, I think, where lab studies are particularly useful because we can reliably image the nucleation process. So for example, this figure on the right shows you a plot of shear stress, which is this gray curve here. This is by Marco Scuderi and others, published in Nature Geoscience in 2016. The shear stress in the fault slip is in black over time for one seismic cycle in the lab. So the stress drop here is the actual seismic event. And the red curve is a continuous measurement of p-wave velocities that are probing through the fault. And what you can see is there's a dip in VP, the p-wave velocity, before the stress drop, which is indicative of imminent failure. And so we see these types of things all the time in the lab, which brings me to my question for the first part of the talk, which is, what are the physical origins of these precursors at the lab scale and in nature, and what do they imply physically or micromechanically? So to do this, we are running some lab experiments and generating earthquakes, which I'll call lab quakes. So these lab quakes that I'm going to discuss are generated in a custom rock deformation rig at Penn State, which is where I did my PhD. And it's a dual-axis servo-controlled hydraulic press where you have a fault normal load applied along the horizontal axis and a constant strain rate applied on the vertical axis. So the sample itself is composed of 3 blocks of granite in this case, although we can use a variety of different things and different configurations. So the 3 blocks of granite sandwiched together form 2 faults that are 5 centimeters long and 5 centimeters wide going into the page. So your rupture area is a 5 by 5 centimeter square. We put a thin dusting of fine quartz gouge to simulate the wear or fault maturity, and then shear this longer central block at a constant strain rate to generate a lot of lab earthquakes. And so I also want to point out here that mechanically, these experiments are incredibly well instrumented. So what I mean is that we have displacement sensors, load cells in the horizontal vertical axis to measure the far field response and the near field mechanical response. And so finally, as we shear the fault, we're also continuously shooting and receiving ultrasonic pulses through the faults, so transmitting, receiving through the fault at really high frequency. And so for these experiments that I'm showing you, we sent and received 1,000 high frequency pulses every second, and each pulse is sampled at 25 megahertz so that we can resolve the P wave amplitude and velocity properly. So why do we do this? Why do we monitor the ultrasonic waves? So to answer this, I want to really zoom into the fault core right here. even if the faults and cracks are look flat and rough macroscopically, on some scale at the microscopic or nanoscopic level, they look something like this. You have grooves and ridges, and you have some degree of roughness. So the high frequency, the ultrasonic waves that I use have wavelengths that are longer than the width of these faults. And so when the pulses are propagating through the rough faults, you have these tiny load-bearing asperities or contact junctions, and they can either pass through an asperity, such as the cluster on the right, or they can pass through a gap where there's no contact junction, like on the left. So when the pulses pass through an asperity, there is fewer transmission losses, and so the elastic wave amplitudes and velocities tend to be higher. And conversely, when they pass through a gap, your amplitudes and velocities are going to be lower, and this is the theory. So when the fault is being sheared, observing these pulse properties can tell us something about the real-time evolution of the frictional contact area, not just the macroscopic contact area. And hopefully this will tell us something about the nucleation process. Okay, so once I run all my experiments, this slide is just showing you what a typical experiment looks like. And the plot shows you fault strength on the y-axis and displacement on the x-axis. So the number on the bottom is just an experiment identifier, so you can ignore that. And the black band here that you're seeing contains a lot of stick-slip cycles or lab earthquakes. So again, just I want to reiterate that this is the really wonderful advantage of these types of experiments, is that we can study the systematics of literally hundreds of lab earthquakes. So this band probably contains 200 to 400 earthquakes in the lab scale, with a full dense array of incredibly high resolution geodetic and seismic instrumentation. So before I start analyzing my results, I just want to show you what these samples actually look like, so you have a sense for size and scale. The white patches on the granite blocks are the wet quartz gouge, which I said was a very thin layer of quartz dusting. And the steel blocks in the back contain ultrasonic sensors, which are stuck to the granite blocks with the use of molasses. So you might even actually be able to see some features in the middle block here that resemble silicon lines in the field. Okay, so going back to the lab experiment, in the next few slides, I just want to zoom into a very tiny portion of the experiment, and we're going to dissect a couple of these lab earthquakes so we get a sense for what's going on during them. Okay, so first, let's look at the shear stress evolution for 3 of these events. The stress increase is the intraseismic strain accumulation, and the stress drop is the actual rupture or the lab earthquake. So in our experiments, remember, because the fault is tiny, the entire fault ruptures each time. So it's like a rigid block, spring block slider type situation. And you can actually hear this, and it typically sounds like a clap or something like that. So next, I'm plotting the evolution of the P-wave amplitudes for the 3 lab earthquakes in purple. And immediately you can see a really nice long-term reduction in the amplitude before the rupture, right? Which is my amplitude anomaly arrows pointing to. And finally, I'm plotting the P-wave velocities in brown. And suddenly we see something really, really interesting, which is that the velocity is also reduced before an event, but the velocity anomaly, if you want to call it that, is not taking place at the same time as the amplitude anomaly. So what's going on here? Because physically, the model that I originally introduced was that the amplitudes and velocities are interlinked. And so based on that, this doesn't make any sense. So what I want to show you is our experimental configuration again, and point out as a reminder that the P waves we're recording sample both the fault zones as well as the wall rock surrounding it. So it's passing through 3 blocks and 2 faults. And so I'm asking the question, can this be the reason for the mismatch in the amplitude and velocity signatures? And so to really find out, we leaned a nonlinear geophysical tool called, I'm sorry, I just have something going on with my microphone. Can you still hear me okay?
Yes.
Oh, I can't hear you anymore.
Can you hear me now?
Let's see. Sorry about that. Can you say something? Sorry, you're muted, Sharon.
Yeah, can you hear me?
I can't hear you anymore. As long as you guys can hear me, I guess that's fine. We can keep rolling. And if you stop hearing me, just let me know. Okay?
Yes. Okay.
Cool. And we can just take the rest in the chat if necessary. Cool. So again, as a reminder, just because we had a bit of a loss in continuity there, my goal with the nonlinear geophysical technique is to parse out or partition the role of the wallrock and the fault zones itself on the variations in the amplitude and velocity behavior. Okay, so this technique is called dynamic acoustoelastic testing, and this was really popularized by a few of our collaborators at Los Alamos National Lab, and Jacques and Parisa, who are the engineering mechanics professors at Penn State. So what we do here is that we basically take a block of granite, the same material as our wallrock, with the same cross-sectional area as the friction experiments and the same length, and subject it to the exact same horizontal and vertical loads as our friction experiments. So to simulate the stress changes due to the stick slip events, we oscillate the vertical loads over a range of frequencies and amplitudes and record the ultrasonic pulses perpendicular to the stress oscillation direction. So we oscillate the vertical stress to simulate a shear load and record pulses in the horizontal direction. So what does the outcome of this experiment look like? So these three plots show the vertical stress oscillations at different frequencies in black and the corresponding P wave velocities in blue and amplitudes in red, with the yellow being the air envelopes. The lowest frequency corresponds to the interseismic period or the reoccurrence interval of our stick slip experiments roughly. And the highest frequency on the right is very close to the duration of our lab earthquake rupture. So what we can see visually, even to a first order, is that the P wave velocities are more sensitive than the amplitudes to stress variations in the bulk wall rock. And so using this data, we can calculate the stress versus velocity and stress versus amplitude relationships. And then using these calibration coefficients, we can calibrate our friction experiment by removing the effect of stressing experienced by the wall rock. And so just to summarize this as a very simplistic set of equations, the friction experiments record the full field response of the two faults and three blocks. And we can subtract out. It's not really as simple as this in reality, but this is a very nice, easy way to visualize what's going on. We can subtract out the response of the blocks using our nonlinear testing method. So what we're now left with is simply the average fault response, which is what we wanted to know in the first place. And before I show you the result of this exercise, I want to recap how to visualize a lab earthquake or generally a seismic cycle by looking at this stress time plot from one of my stick slip experiments. So we can bifurcate the stress into an interseismic, a pre-seismic, and a co-seismic phase. And this is going to be different. This bifurcation is different from what you might see in the field by seismologists. And so the interseismic to pre-seismic partition that I designate is based on where the shear stress increase becomes nonlinear and deviates from the loading stiffness, because that is the point at which we think pre-seismic creep should onset. Okay. Finally, now we can see the result of the two sets of complementary experiments. The top plot shows the P wave amplitude, I normalize it and call it a transmissivity versus time, and the bottom plot has the P wave velocity versus time. Now, remember the deep blue lines are the fault zone response only after the calibration exercise, whereas the black lines are the raw data from the friction experiment. So first, we see that the onset of amplitude or the amplitude reduction and the amplitude trends overall barely change regardless of if you look at the bulk or the fault zone response. And so what this means is that the amplitude changes that we document are entirely coming from the fault alone. Now, this is not the case for the P wave velocities, because remember, the bulk velocity has a very short-term anomaly just before failure. But the interesting thing is that when we partition out the role of the stress increase in the wallrock, the velocities now look very, very similar to the amplitude response and has a long-term reduction now. What this means is that the P wave velocities contain information about the state of stress on the fault. And so probably as the stress increases, the cracks in the wallrock are elastically closing in our experiments, and the bulk system is stiffening. So this is why I say the seismic velocity in this case is acting as a stress meter. And so this still leaves us with an outstanding question about the origin of the P wave signature in the fault zone itself. So why is the shape of the P wave amplitude and velocity of the fault the way it is? So, okay, this plot has a couple of things going on, so we're going to take it slow here. Again, I have a familiar stick slip stress increase in black for one of my experiments. And the P wave amplitude is in purple, and the slip rate of the fault itself is in green. So I have the loading rate annotated as well for convenience. What we're seeing is that the seismic amplitude essentially mirrors the fault slip rate. So as the fault starts to have accelerated creep before the eventual lab earthquake is when the amplitude starts to reduce. So thinking back to the original model for a real contact area, what this means is that as the fault slips faster, when the earthquake nucleates or you have a very long nucleation phase and a seismic creep phase, the real contact area decreases and drives the pre-seismic P wave amplitude and velocity reduction. So what does this mean for crustal faults, which are much, much, much more complex, right? And before we get to that, I just want to give a shout out to some of Chaz's work, which is very complementary to what I'm showing here. But these are acoustic emission studies instead of active source studies. So what this means is that instead of having a transmitted wave that is passing through the faults and being received on the other side, instead we're passively just listening to microseismicity in our fault, which is what we call acoustic emissions. So this plot on the left is simply a counting exercise. So it just has the AE rate or rate of change of acoustic emissions per second in time, or in this case, per micron in slip for a driving rate of 0.3 microns per second. So again, you have a couple of stick slip cycles, and what you see is that the acoustic emissions continue to increase as we are almost about to, the fault is about to fail. If you look at the actual AE wave train itself, which is what this plot is showing here, so shear stress in black, and this is the variance of the acoustic signal, but we'll get to that in a second. If you look at the actual acoustic emission wave train itself, this is just the raw AE data during our experiment. You can see that there are fewer events earlier in the cycle and more larger events later in the cycle before the eventual failure. The variance is just a more convenient way to think about these metrics because it's literally just the statistical variance or the square of the energy content in a moving window of these acoustic emissions. So what that shows in blue is that the variance is increasing before failure, just like our pre-slip trends. So as the fault starts to pre-seismically creep, there's more and more energy culminating in an eventual large seismic rupture. Another way to look at this lab study is to think about the B value of these acoustic emissions, because what they are is essentially microseismicity. And the B value of the lab events for our study on the left here also decreases before failure as the fault slips faster and faster. I also have Thomas Gobel's study from 2013 here, just as a comparative study, where they also documented that the B values decrease consistently before the actual lab stick slip or lab failure. There's a couple of really cool standout things for me, is that these two studies represent incredibly different apparatuses, different driving rates, and more importantly, different stresses. So our experiment was conducted on granular fault gouge at a stress of about 3 MPa, whereas this study by Thomas Gobel and others was at a differential stress of 200, 250, 300 MPa. So this represents an almost 100x difference in stress, but the B values are practically the same, which indicates that the B value is dependent on these frequency magnitude statistics of these events largely depends on the ratio of your stress to the fault strength rather than absolute value of stress itself. And also that it depends on these other conditions like the slip rate on the fault and stressing rate and so on, which I think is really fascinating. Okay, back to trying to understand the crustal or the lithospheric significance of what I've told you so far. And so to answer this, we're going to take a quick trip to Italy on this map here, where I want to talk about the 2016 Amatrice North Shear Viso earthquake sequence. And this was a pretty complex multi-fault rupture that began with the magnitude 6.1 Amatrice earthquake to the south, then the 5.7 magnitude Viso earthquake in the north, and finally the 6.5 North Shear earthquake in somewhere in the middle. So on the right, the plot shows a time since the Amatrice earthquake on the x-axis, and I'm marking the dashed vertical line to mark the final earthquake in the sequence, the 6.5 event, on day 67. So on the y-axis, you have a percent change in the p-wave velocity at 2 seismometers, which are colored red and blue on this map here. So red seismometer, red dots, blue seismometer, blue dots. So these p-wave velocities are not from an active source study. They are from a time-lapse crustal tomography that was done using teleseismic earthquakes that happened very far away during these 70 days and sampled the lithosphere in this area. So it's what this group, Claudio Chirab and others, saw is that at the red seismometer, which is close to the North Shear earthquake hypocenter, there was a p-wave velocity reduction for about 20 or so days leading up to the event, which they interpret as the nucleation process. However, the really interesting thing is that they don't see this precursory signature on the seismometer further just to the north, right? This is just increasing consistently. Now, compare this with what I've showed you in my lab scale study on a really tiny 5 centimeter fault on the left, where I have the same X and Y axis for my lab earthquakes. The red curve is the fault zone p-wave velocity, which tracks the pre-slip and the nucleation process. And so you can see a clear precursory reduction. And the blue curve is a raw signal from my friction experiments, which additionally tracks the stressing of the wall rock as well as slip on the fault. And you can't see the precursory nucleation signature too clearly. So what these two observations collectively tell us is that lots of earthquakes in nature might have these types of precursory phases, but their signal may not be strong enough because it's drowned out by other signals, like from tectonic loading, especially in the far field, as this shows. So what I'm making a case for is denser instrumentation or hyperlocal studies in high-risk areas, but also that we need to come up with really clever ways to quantify and correct for these external tectonic loading signatures. Okay, So the summary for this first part of my talk is that changes in the seismic wave properties contain a lot of rich information. I hopefully have convinced you of this idea. And about the state of stress in the crust, as well as the earthquake nucleation process. And going forward, I want to think about leveraging this for quantifying earthquake risk and forecasting. Okay, in this second part, which I'll probably spend another 15-20 minutes on, is something that I worked on at the tail end of my PhD, as well as something I'm working on right now at the Institute for Geophysics at UT, is trying to understand slow slip events in subduction zones. With Chris Marone, Damien Safer at UT, Laura Wallace and Luc Lavier at UT as well, and Matt Ikari at the University of Bremen in Germany. So what I'm interested in is the study of slow slip events here, especially in subduction zones, which, as many of you may know, are basically an entire family of earthquakes that are far slower than your conventional, dynamic ruptures, and these can last for many weeks, months, and so on, rather than just a few seconds. And we're still not entirely, as a community, clear on whether slow slip events represent the same thing as regular earthquakes, or if they represent fundamentally different mechanisms. So one of the questions that I'm interested in asking is simply, why are slow slip events slow? And without getting into too many details, certain frictional properties determine whether a fault can nucleate an unstable earthquake, or if it's going to prefer to creep quietly. Now, the first requirement is that the fault strength decreases as it slips faster. And we would call this velocity weakening friction. And this is a necessary condition for earthquakes. So in this plot on the top left, when I increase the sliding speed of the fault in an experiment, the friction first increases and then decreases to a new value. So what my first requirement says is that this new strength has to be lower than the previous value. And we measure this in the lab as this A minus B term. So this change in strength will take place over a distance called d sub c, which is this here. And this is directionally proportional to this LC or H star length scale in earthquake nucleation models. The second requirement is that the fault is able to heal or store strain energy interseismically. So what about the energetics of the rupture? This is also important. And I'm going to talk a little bit about rupture energetics in this slide and the next one. So on the right, we have a spring block slider setup. And on the left, you have a corresponding fault friction response. So starting from the top, we have a block that is sitting on a surface and it's being pulled by a stiff rod. Okay. And so progressively, as we go down, we have a softer and softer spring. So when we pull the steel rod, the block slides aseismically because it is very, very stiff. So the K, or spring stiffness from a Hooke's law perspective, is very high. Now, as you make this spring softer and softer or more flimsy, you get a more pronounced stick and slip instability behavior, which grows in intensity because you're now reducing the spring stiffness and pushing it. So this ratio of K over K sub C, or a critical stiffness, is less than 1. So the stiffness at which the fault transitions from a stable creep to starting to produce stick and slip instability is what we call a critical stiffness, or K sub C. And this is really important from an energetics perspective. And mathematically, you can express K sub C as essentially the inverse of this d sub c term. And in the numerator, you have an effective stress and this A minus B that I introduced earlier. So another way to think about K sub C is simply as the reciprocal of this LC or the H star term. So Kc is a critical stiffness, whereas Lc is a critical nucleation length scale, and they have opposite effects on the rupture energetics. So the question that I'm asking in the second part is simply, why is slow slip slow? And so for that, I go to the Northern Hikurangi margin, which is a somewhat unique natural laboratory to study shallow slow slip events because of how well instrumented it is, and because the SSEs propagate very close to the trench, which makes sampling the source somewhat easy. And so in the Northern Hikurangi margin, the Pacific plate is subducting beneath the Australian plate at around 45 millimeters per year. And the shallow SSEs we have here have quite small stress drops and relatively short reoccurrence intervals of 12 to 18 months or so. And so the source region for these SSEs coincide pretty well with a high reflection zone and active seismic data. And it's typically inferred to be a region of high pore fluid pressure. So we sailed on expedition, IODP expedition 375, where we drilled a few sites, sampled material that we think may be eventually being subducted and participating in the slow slip events. And these are the samples that I run my friction experiments on. Okay, so I moved to a somewhat different configuration here from what we discussed, and we conduct friction experiments on a couple of different apparatuses so that we can probe the full range of slip rates from plate rate, which is 10 to the minus 9 meters per second, to faster than slow slip rates, which is about 1 millimeters per second. So the apparatus on the left, which is the biaxial deformation rig at Penn State, takes care of slip rates that are relatively faster, around centimeter per day. And the apparatus on the right takes care of very, very ultra slow slip rates, which is centimeters per year, or tectonic plate rates. In both cases, the rigs work in pretty similar ways, in that you sandwich the sediment whose frictional properties you're interested in between metal rams in a hydraulic press, and shear the sediment sample at constant background rate to mimic the tectonic loading. In the case of the biax, you have two faults, and you take the average response of the two. And in the plate rate apparatus, or the single direct shear apparatus, you just have one fault that you're shearing. So in both cases, the fault is sitting in a fully saturated state at a constant pore pressure and a realistic stress state. In the biax, you have the luxury of having a relatively, an essentially true triaxial stress state, whereas here, that is not necessarily the case, but the effect is the same. Okay, so in both cases, we run friction experiments, and all of these different dots represent experiments that we conducted on different lithologies. So the purple and the orange represent lithologies that are relatively carbonate rich, whereas the two greens represent lithologies that are more clay rich. So what I'm plotting here is the frictional stability A minus B, as well as the critical slip distance D sub C, as a function of a velocity step that I showed you earlier. What I'm showing you here is that, well, before that, actually, I should remind you, a positive A minus B represents a velocity strengthening fault. And remember, this cannot nucleate an unstable slip or a rupture. You need velocity weakening friction, which is negative A minus B, to get unstable slip. So what we observe is that the A minus B is relatively velocity weakening or velocity neutral, and transitions to velocity strengthening as your slip rate increases. And the D sub C, which is on a log-log plot here, is also increasing with velocity, which somewhat goes against the prevailing view of a constant A minus B and D sub C. And this behavior is apparently relatively independent of lithology. And what I mean by that is that even though we've tested a range of lithologies, they all have similar velocity dependent friction. So in the context of critical stiffness, then what does this mean? What this means is that as the rupture nucleates and the fault is accelerating, DC is increasing, right? And this would decrease the critical stiffness and potentially make the fault stiffer than the critical stiffness. And so at this point, mechanically or energetically, it is no longer favorable for the fault to be unstable, and instead it's going to creep aseismically. So this works really well on paper, but I'm curious, then the question is, how does this translate to a real fault? And for that, I just want to give a quick shout out to some of the work that one of my collaborators, KJ, who is a postdoc at Caltech, recently did in a 2020 paper in Nature Geosciences, where he modeled these types of velocity dependent friction on a 1D spring blocks slider model. So this is a plot of normal stress versus slip rate for two cases. On the case on the left, you have constant frictional parameters. So A minus B and D sub C are constant versus velocity. And each of these white dots points represents one numerical simulation on this type of a Hookean fully elastic spring block slider. So deep red means that the instability or the lab earthquake stick slip velocity is high, and the blues mean that the velocity is low, approaching slow slip rates. So in the case where everything is constant, you can see that there's a very strong bifurcation. So if the fault is stiffer than a critical value, it just slides stably. And if it's even slightly softer than the case of C, then you have unstable dynamic rupture. So in this scenario, you basically cannot get slow slip at all. But if you make the frictional properties of the fault velocity dependent, now suddenly you have a pretty wide range of parameters, both effective stress as well as slip rates or driving rates, strain rates, where slow slip can be accommodated or survive in a spring block slider. So then one of the questions I had was, how does this translate to a finite length fault, which has depth varying properties? So to do this, we modified a Burge knop-off style model where you have a series of spring block sliders that are connected to a rigid plate that is being driven at plate rate elastically. And then the blocks themselves are connected to each other with a viscous dashboard. And this interface has radiant state friction. Then you do that. These quasi-dynamic rupture models also confirm that velocity dependence of frictional stability and d sub c favors slow slip. So the y-axis is time, x-axis is distance down dip or distance along the fault. Deep blues in this case indicate velocities. The deep blue is a locked fault. Light blue is, or zero corresponds to being driven at plate rate. And the deep yellow means the darker the yellow, the faster the slip rate. So when all of my frictional parameters are constant, I have a rupture that starts here in space and time and basically nucleates in hundreds of seconds and propagates through the entire fault. Now, when I make the A minus B and D sub C velocity dependent, like my friction experiments, now suddenly the rupture lasts for tens of days, starting from here and propagating very, very, very slowly. So I've essentially turned a fast event slow. Okay, so going back to the conceptual idea, or asking the question conceptually of why is slow slip slow? We'll consider the earthquake nucleation process again by using Greg's space-time plot, which hopefully we're all familiar with by this point. What you have is an instability that gradually grows outwards in space until it becomes dynamic, as a reminder. Now, if we take one location on this fault, we'll just take a cross-section along this dotted line. In the traditional view, you have a critical stiffness and a fault stiffness that are both constant in time. And so what that gives us is an instability that grows until it hits dynamic weakening processes like shear heating and so on. And so you get really high slip rates and the event becomes dynamic. This is what a regular earthquake is. In the new view, slow slip is slow because the variation of critical stiffness due to increasing A minus B and D sub C makes the instability rate limiting. So as it grows, the critical stiffness reduces, and this in turn makes the fault slip slower and slower and never allows it to go fully dynamic. So at some point, all the stored strain energy in the spring is completely depleted and it runs out of energy. So essentially in this view, a slow slip is a prematurely arrested dynamic rupture nucleation phase, which was never allowed to go fully dynamic. Okay, so I've said and shared a lot of things. So understandably, I guess everyone's a little tired at this point, and I want to just wrap up my talk by with a couple of summary slides. In the first part of my talk, I was talking about how we can image the earthquake nucleation process, and I said that pre-earthquake variations in elastic wave properties, amplitudes, velocities, etc., can contain a lot of information about both the stress state and the slip rate on the fault. And in the second part, I introduced slow slip events as a very long-term and prematurely arrested dynamic rupture, which frictionally the velocity-dependent frictional properties, A minus B and D sub C, make it so that it is energetically unfavorable for a rupture to become dynamic in this framework. And so I'll stop here and take any questions. Thank you so much. And just as a reminder, it sounds like I cannot really hear you. I don't know if that's changed.
Can you hear me?
No, I'm not able to hear you. Actually, let me do something here really quick. Can you talk now? Maybe I can hear you.
Yeah.
Yeah.
Okay.
I can hear you. That's great.
Yeah. Thank you, Srisharan, for such a nice talk. I think we have a question on the chat. Navin, can you? Okay. So we have a question on the chat. So it says,
Yeah.
how can we? Yeah, you can read it.
Yeah. How can we separate the seismic cycle as pre and interseismic in the case of? Yeah. So this is something that I've. Okay, let me just read out the entire question in case people are listening in. How can we separate the seismic cycle as pre and interseismic period in the case of lab earthquake experiments? Are there well-established bases as in the case of natural earthquakes? So I think that's a really interesting question and a somewhat, let's say, I guess, problematic almost in the lab scale because I'm just going to stop sharing and show you my relevant slides because I guess the short answer is no. What we do in the lab in terms of separating as a pre or interseismic is somewhat arbitrary compared to what you would have in nature, because in the lab, I have the advantage of having an incredibly long pre-seismic stage. See, in the lab, I have what is essentially 60 or 70% of the inter-earthquake time is pre-seismic, where you have pre-slip or creep. In nature, you don't really have that luxury, right? Pre-slip might happen for a couple of seconds, couple of minutes, couple of days at most. And the pre-seismic moment release in nature is also less than 1% of the total cumulative seismic moment release, best we can tell. Whereas in the lab, my pre-seismic moment release can be sometimes up to 5 or even 10%. In these experiments, the pre-seismic moment release is basically 5 to 10% of my co-seismic moment release. So I don't know that there is a clear, let's say, relationship between what we demarcate as pre and interseismic in the lab versus what you would do seismologically. I don't think there's a good way to do it.
Yeah, thank you. So I have one question on the same slide, 26. Here you saw that the A rate during the experiment is kind of linearly increasing. So I was expecting that it could be more like exponential increase when we increase the shear stress.
Oh, you mean this is increasing linearly and you?
Yes.
And you think it should be more exponential?
Yeah, I mean, just my basic understanding, because as we increase the shear stress, the rate of A should be increasing in the same way.
Right. I guess.
Because the experiment that I have and I'm working on, so it has like when I plot the same plot, then I have more like exponentially increasing A's before
Okay.
the failure. So.
Sure. Yeah. I'm curious if so. The thing is, this AE increase rate depends on a lot of things. Well, first off, I don't even think it's linear because this is a log scale, right?
Oh, okay.
So that it may be that this is consistent with what you have in your experiments as well. But also, I would comment that AE rate is dependent on the sliding rate. I wish I had all the other panels of this. This is only at 0.3 microns per second, but we have a few other strain rates. And the AE rate in some cases takes off, and in some cases it just there's no change in AE rate at all. So it depends on the strain rate. It also depends on the material, right? Because when you have experiments on just bare rock surfaces, there's hardly any foreshocks. So it's not that we cannot. It's not that our cataloging procedure is inadequate. It's simply that there is no foreshock at all, even if you go very, very close to the fault. So in that case, the AE rate is maybe not increasing as much, except very close to failure, and it just suddenly takes off. So I think there's a lot of different considerations, lithological, boundary conditions, and so on.
Yeah, and can you go to the slide where we discuss about the wallrock effect and fault effect?
Sorry, say that again. What effect?
Wallrock effect, wall effect.
Yeah, let's see. Maybe this one, like this, or
yeah, so
maybe
yeah, this
this
one.
one.
Yes, 24. I couldn't quite understand how this, what effect had the wall, so that make this velocity, py velocity and amplitude so different. The curve on the right.
Oh, so you're asking mechanically why?
Yes.
Yeah, that's a really good point. Like, if your question is why the velocity variations are so much more prominent than amplitude variations, like, well, why velocity depends so strongly on the stress versus the amplitude, I don't have a great answer for that. I think partly it could just be that there is the velocity depends on uh, elastic modulus, right? And so when you're increasing the elastic modulus by essentially triaxially increasing the differential stress as well as the you're increasing both P and Q essentially. And so when you do that, I think that has a stronger effect on the elastic modulus and in turn the velocity, whereas that same effect is not felt on the attenuation or the amplitude. So that's my best guess, I would say, but that's a really good question.
Yeah, and in the same slide, so we talked about wall-rock effect for velocity, and when we subtract it, and then it is more like similar to what we have for P wave amplitude. So don't you think like the wall-rock effect has some effect on the P amplitude as well?
Yeah, it does. It has a very small effect on the amplitude, but it's not, all things considered, it seems like it doesn't fundamentally change. Basically, this stressing, right, or the elastic closure, if you want to believe, of cracks in the wall rock don't have nearly the same effect on the amplitude as it does on the velocity. And we also have to remember these are all relatively dry experiments. Like, these are in a completely humid chamber. My guess is that if you include pore fluid and filtration into the mix, you think the fault zone is fully saturated and has a finite pore pressure, I think the story might change significantly, and you might see a strong effect on the amplitude as well. You might have to start thinking about, maybe instead of VP, you have to think about VP-VS ratios or something like that. So this is only, in my view, a very small part of the story.
Yeah, thank you.
Yeah.
Any more questions from other people? Yeah, I have one more question. Like, In your first or second slide, I forgot where you have the experiment set up.
Yeah.
So how many sensors do you use? So it is active source experiment, right?
Yeah.
How many sensors did you use and like in which locations? And
Okay, so I have a P sensor. So in this case, in these experiments, I use 3 sensors. I have a P up here and a vertically polarized S sensor and a horizontally polarized S sensor. So it's like basically like a triangle. There are some other experiments, like for example, it really depends on which one. Like these experiments, you have a full array of sensors. I use a different sensor block. So the entire block, the metal square block, is covered with P sensors. So it's a 9x9, not a 9x9, so 4x4 grid of sensors. So it really depends on the experiment. So the answer is anywhere between 1 and 20, maybe.
okay. So did you look for how it looked when you chose the diagonal sensor pair?
Yeah, that's a good point. Actually, that's something that I'm working on right now, is to look at, that's not a good plot, but to look at cross-cutting sensors, at different angles, whether there is a higher or lower variation. And it seems like there's some subtle differences between wave paths, ray paths, essentially. But I don't think I have a clear, definitive enough answer. I've looked at it and I continue to look at it.
Thank you.
Yeah.
What's the input signal? Is it P wave only or is it PNS?
So for the P to P sensor, it would be just the P. For the S to S, it would be horizontally polarized or vertically polarized S, and so on. So it depends on the sensor. We determine what input signal to give, both the polarity as well as the size of the input signal.
Okay, then I think we have all our questions answered, and thank you, Dr. Sridharan, for for being in our seminar series.
Thank you so much for inviting me and having me.
Yeah, thank you so much for such a great talk.
Thanks.
Yeah, thank you. See you later.
Yeah.
Bye.